The objective of this video is to introduce performance measures for power electronic converters. Specifically, we're going to be talking about line regulation, load regulation, and efficiency. The idea here is to introduce you to the terminology that's used to describe the performance of power electronic converters. In order to work in this domain, in order to design these converters, you need to be familiar with the terminology that's used to describe how they behave. So if we start by considering the desired behavior converter, we can label this, for example, the desired set point. And this can actually refer to any quantity. Perhaps it refers to voltage. Perhaps it's the value of 12 volts. Perhaps it's a current within a converter. Maybe it's a power output or input. It could be a speed. It could be a rotational speed if you're operating a motor. But say it's a voltage. We might call this value V star. And depending on the quantity that we are talking about, it might not be referred to as a desired set point. It might instead be referred to as a nameplate value or a reference value or the nominal value. So when you have a desired value that you want to operate at, you need to acknowledge that you don't actually always operate at that point. So perhaps our desired value is V star, but our actual value is V. And that's to say that our actual value deviates from our desired value. So when we say this, what we really mean is that we have some error in our system, and our error can be calculated as V star minus the actual value, V. And it's oftentimes useful to normalize this as a per unit value, which can be done as follows. Or you can instead express this as a percentage by multiplying by 100%. Okay, so now we've talked about a desired or a nameplate or a reference value. We've acknowledged that we actually may get something different and defined an error. Let's now talk about regulation. The act of regulation is to try to drive this error down to zero. If you have 0% regulation, that means that there is no error. Your actual value matches your desired value at all times. And when we talk about regulation for power electronic converters, typically we're talking about one of two types of regulation. We're either talking about line regulation, or we're talking about load regulation. And line regulation is so named because it refers to changes in your output behavior due to changes in the line. So, for example, we can be talking about changes in output voltage due to changes in the power grid line voltage. And similarly, load regulation is named this because it refers to trying to regulate errors due to changes in the load. And always the objective or the desired result is that we have 0% regulation, which means that we have no error. Okay, so let's consider an example. Let's talk about the single-phase rectifier that we've been building up so far in this class. And in one of our previous videos, we developed the following expression that we use to actually solve our series resistance value. But in this case, we're going to use it to solve for our output voltage. So we can take this expression and we can simplify it down to allow for some illustrative conclusions. So this first term here, we can say that this is approximately equal to 1. And we can recall that our VDC equivalent voltage is actually our VDC value, which is our output voltage, plus 2 times VD, where VD was our voltage drop across our diodes. So if we rewrite this expression, we can say that VDC is approximately equal to the following. And in this expression, we can note that VDC is our output voltage, Vs hat is our line voltage, our input, and IL is our load current, assumed to be DC. So we can see from this that as our line input changes, as Vs hat changes, VDC will also change. That means that we have no line regulation. As our line changes, our output voltage will change. Furthermore, as our load changes, as IL changes, our output voltage will also change. So we have no line regulation and we have no load regulation. So we can see from this that the passive rectifier simply cannot give us a regulated output. So why does this matter? Well, you can imagine that if you have a light bulb on this, for example, and somebody turns a hairdryer on next to you, the line voltage may sag and the light bulb would dim. This can be very detrimental for sensitive electronics. So we can take these quantities and we can actually make a graph. We can make a plot of VDC as a function of our line voltage, Vs hat. And it's going to look something approximately like this, where perhaps at this point right here, we have our VDC star that we desire, which corresponds to one value of our input voltage. But as we change our input voltage, this VDC output will go up and down this curve. And we can then say that right here corresponds to our ideal behavior, but this corresponds to our actual or real behavior. So a graph like this is called the input characteristics of the system. We can similarly draw a graph of the output characteristics. So we can see how VDC changes as a function of IL, and it's going to look something like this. And perhaps right here corresponds to our ideal case, VDC reference. And we'd like VDC, again, to behave according to this straight line, where it's insensitive to changes in our load current, but in actuality, VDC is going to go up and down this line according to the equation that we drew above. So what do we do? Well, if we really need a regulated output, which is very frequently the case, we can add a linear regulator to the output of this, as we discussed in a previous video. So remember that we drew our linear regulator as an equivalent circuit of a voltage divider. And on the input of this would be our VDC unregulated. And on the output of this is our VDC regulated. And our load just appears perhaps as a current source. So with a circuit like this, we can obtain approximately 0% regulation. What does that mean? That means that our VDC value does not change with respect to line input, and it does not change with respect to our load output. All right, the final point I'd like to talk to you today about is efficiency. And we can consider efficiency by looking at the following block diagram, where we have some amount of power going into a black box. I'm going to label this black box as a power electronic circuit. And we have some kind of useful power coming out of this circuit, P out. In the case of a power electronic circuit, we typically will have some kind of input voltage, input current, and then an output voltage and current. Perhaps these are different values. So P in and P out are related to efficiency as follows. And if efficiency is not 100%, then there's some loss somewhere, and we can represent that here. This will be a useful relation as you solve power electronic circuits going forward in the class. Remember, you can always write P in is equal to P out plus P loss. And you can always relate this back to the input and output voltages and currents.